Today we're going to be talking about the chi-square test. I am Drew Gartner. I worked with Lindsay Reichs and Paul Fredericks. Let's say that you have a coin that you're going to flip 6 times. You flip it, you would expect the result of 3 heads and 3 tails, or 50% heads and 50% tails. Now let's say in practice you flip it and you get the result of 2 heads and 4 tails, or 33% heads and 67% tails. The question is whether or not this is a rigged coin or if there's some sort of result due to chance and you are wondering whether or not this coin is fair. This leads us into the purpose of a chi-square test. Chi-square tests are used to determine if inconsistencies between observed and expected number of progeny is statistically significant or not. In other words, if the difference between the observed and expected numbers is by chance. Here are some terms to know if you are going to learn chi-square test. The first is statistically significant, which is the likelihood that a relationship between 2 or more variables is caused by something other than chance. The null hypothesis, the hypothesis that there is no significant difference between specified populations, any observed difference being due to sampling or experimental error. And p-value, calculated probability that your data fits the null hypothesis. Progeny, the offspring of a person, animal, or plant. Genotype, the genetic constitution of an organism. Phenotype, observable characteristics in an individual resulting from its genotypes. And degrees of freedom, number of phenotypic classes minus 1. So then the next question becomes, how do you actually perform the chi-square test? So I will work you through the steps. The first step is to count the number of results of genotype's observed distribution, or O value. Then you calculate the expected number of genotype distributions, E. Then you use your E and O values of each genotype into the equation chi-squared equals observed 1 minus expected 1 squared over expected 1 plus observed 2 minus expected 2 over squared over expected 2. And you can use this for any number of genotypes, including 1 or more than that. You can calculate the degrees of freedoms, or phenotypes, which is phenotypes minus 1, and you compare the chi-square values at degrees of freedom, and then you interpret the results from there. Now, how do we actually calculate the expected number of progeny? A Drosophila with genotype big B little b, a wild type I phenotype, is crossed with a Drosophila with genotype little b, a white eye phenotype. They have 120 F1 progeny. You can calculate the F1 genotypes using a Mendelian square, which gives you the results of 4 different types of big B little b, big B little b, little b little b, and little b little b. This is a 1-to-1 ratio of genotypes. For a 1-to-1 ratio, you would expect equal numbers of progeny for each genotype. So for the expected progeny of big B little b, you would get 120 divided by 2, or 60 big B little b, and the same is true for little b progeny. You would have 60 little b progeny. Now let's actually try and calculate some values. The actual progeny obtained from the cross contained 55 progeny with a big B little b genotype and 65 progeny with a little b genotype. So we enter in our 2 different genotype results. Our observed numbers, which again was 55 for big B little b and 65 for little b, and compare to our expected values, which was 60 for each. Then you do the first part, which is observed minus expected squared. So for big B little b, that would be 55 minus 60 squared, which is 5 squared is 25. Then 65 minus 60 for little b is 5 again, squared is 25. Now remember that the chi-square is the sum of those values divided by the expected number values. So we take our 25 and divide them by 60, giving us a 0.42 for each of the genotypes, and we get a 0.84 value for chi-square. Now we need to be able to calculate the p-value, and to do so we need to have the degrees of freedom, again for wild type eyes plus white eyes, minus 1, which is 1 degree of freedom, and recall that our chi-square value is 0.84. So then we come over to a percentage points of the chi-square distribution table, which says that there gives you a wide range of degrees of freedom starting at 1 all the way to 60, and you could calculate even more than that. Then you take your degrees of freedom and your chi-square value, and you find where your chi-square value falls in between the top line probabilities at the given degree of freedom. So for our example, we have 1 degree of freedom, and our chi-square value of 0.84 falls within a p-value of 0.5 and 0.25. Now we can use this data to determine whether or not our results are statistically significant or not. At the end of the chi-square test, you receive a p-value. If the p-value is greater than 0.05, the inconsistencies are not statistically significant, and the differences are due to chance. In other words, you keep the null hypothesis. If they are less than 0.05, the inconsistencies are statistically significant, and the differences are not due to chance. In other words, you reject the null hypothesis. Let's interpret the results from our test. Well, again, our p-value was between 0.5 and 0.25. In order to reject the null hypothesis indicating that the differences between the observed and the expected progeny is statistically significant and not due to chance, the p-value would need to be less than 0.05. Since the p-value is not less than 0.05, the null hypothesis can be retained, and you can conclude that the inconsistencies between the observed and expected progenies are due to chance. Now let's take this back to our coin example at the beginning and think about whether or not our coin was rigged. Again, let's revisit our expected results of 3 heads and 3 tails. Then we take our observed data, which is 2 heads and 4 tails. Then we need to use our chi-square equation, which gives us a 2 minus 3 squared over 3 plus 4 minus 3 squared over 3, which gives us a chi-square value of 0.667. Again, we need to calculate our degrees of freedom, which was 1. Now, coin flips are not a phenotype, but they are 2 different unique results that could happen. So you take the 2 unique results and subtract 1, which gives you the degrees of freedom of 1. And then you go back to the table, which I have done for us, which tells us that our probability falls between 0.5 and 0.25. So then we have this number, and we can consider what the implications for this are. And we can recall that if our p-value is less than 0.05, our results are statistically significant. However, our results of coin are due to chance because they fall between 0.25 and 0.5, which indicates they are not statistically significant. You may be wondering, why does the chi-square test matter? And that is a reasonable question. Well, the first reason is that it helps biologists understand distribution of genes. They use the chi-square test to determine if the gene follows known distribution patterns, helping better understand genetic information as inherited and distribution of genes on chromosomes and understanding Mendelian connections. It also can be applied to modern code-breaking problems, helps determine the highest probability measures of decryption of information. Now here is the link to our survey. Thank you all very much for spending time and watching our presentation, and I appreciate the comments and people taking the survey. Thank you very much.